Welcome to this live webinar on overview of MPD well designed by Mr. Nitin Kulkarni, drilling engineer with specialization in MPD and UBT techniques. Thank you for joining in this workshop. Now, without wasting any further time, I would like Sir Nitin Kulkarni to start this introductory session. Thank you. Over to you, sir.
Yeah, thank you, Niharika. Thank you, Nikhil. Am I audible? Are you able to hear me?
Yeah, it's perfect, sir.
Okay, good. So thank you very much for organizing this webinar, and have a greetings to all the participants. Thank you for joining this session. Just to give you a quick background of me, basically, I used to work as an MPD engineer before with Weatherford, and then briefly with Schlumberger. And then later on, I joined oil companies where we were actually deciding on whether we can use MPD on certain wells. So initially, we were from the I was in the service side, then actually in the oil side where we could utilize this technology. So that way, I had an opportunity to see both sides of be on both sides of the table. Where one is when you propose to use this technology to drill a particular section of the well, and then you also are on the other side where you get the feedback and you discuss with the management, you make a proposal to basically get the approval to see if the management is interested and is going to approve this. The geoscience team, the completions team, everybody in the oil company needs to agree before we can go ahead. This involves a certain modification to the conventional method. Now, today's webinar is an overview of well design. So we focus on the well design aspect, assuming that we are going to drill a well, a particular section of the well using MPD. We will basically, we will review certain aspects of what changes we need to do in the particular well design. So certain changes are to be incorporated. And as this is usually important when you are in the beginning phase, but as you move along and as you develop this technology for your field, for your drilling operations, then these things become part of the routine procedure. But this is particularly important when you are doing it for the first time, when you are doing it in the very initial phase. And as I said, if you are doing multiple wells, then on the second well, third well, fourth well, these all become routine procedures and everybody becomes familiar with the process. So today's webinar, the agenda is basically we will have a quick introduction of managed pressure drilling. We will review the difference between conventional drilling, managed pressure drilling, and basically you underbalance drilling, because these two technologies are sometimes confused with each other. Earlier there was underbalance drilling, then the evolution of UBD was MPD. However, the application there is a difference in the application. So we will discuss that. We will also talk about wellbore pressures. So the topic is managed pressure drilling. Now, what pressures are we trying to manage? What we can manage, what we cannot manage. These are the points that we will discuss. And we will talk about variants of MPD. We will talk about the hydraulics of MPD, procedures that are associated with MPD, and we will conclude with the dynamic well control procedure. So sometimes for those who have been involved in the operations, they might be familiar with the fact that MPD as a tool can definitely enhance your well control capabilities. So what it does exactly is what we will discuss in this last part, where we draw the line, because conventional well control is still what needs to be kept in mind, and this is something that needs to be used in the event of a well control. But MPD does enhance. MPD can definitely aid in certain situations, and this is exactly what we will see. There are different tools that have been formed. We will review those. So let's get started. IADC has given a definition. Most of us would know this, but for those who are relatively new to the topic, IADC has given a definition for MPD, which says that it is an annular, it's an adaptive drilling process used to precisely control the annular pressure profile. The objective is to ascertain downward pressure environment limits and manage hydraulic pressure profile accordingly. So the objective of MPD is to avoid any influx from formation fluid into wellbore and to surface. But however, if you get any influx, this will be contained and through an appropriate process. And the process is nothing but a managed pressure drilling process. So this is basically definition and purpose of MPD, clearly defining what we do with MPD. In underbalance drilling is different. So MPD, how is it different from conventional drilling? You see here, this is a simple equation for bottom hole circulating pressure, BHCP. So BHCP is a function of hydrostatic pressure and friction pressure, and we will discuss all this in our course as we go along. But for those who are already familiar with drilling operation, they would know that hydrostatic pressure is static pressure in the wellbore, and friction pressure is the pressure that is due to your pumps. As you start circulating, you get additional pressure in the system, and that is called as friction pressure. But so in conventional drilling, you only have two options, basically to change the pump speed or to basically adjust the mud weight in the well in order to change the bottom hole circulating pressure. And both the options are, especially changing the mud weight in the hole is not an easy option. This can take some time. But what MPD does is it provides an additional function, which is a surface pressure. Now, in this case, you can change the bottom hole circulating pressure if required by adjusting the surface pressure and by keeping the other two pretty much the same, or you also have the option to adjust those pressures. So by introducing this additional function, you can manage the pressure profile in a more precise way. Here is this plot that shows a fundamental difference between conventional drilling, managed pressure drilling, and underbalance drilling. Now you see here in conventional drilling, you have the red dotted line here on the extreme left basically shows your static pressure in the well, and the bold line, the dark line shows the dynamic pressure. So as you start circulating, you shift from static to dynamic, and here you see that there is a risk of exceeding your fracture pressure. If you exceed your fracture pressure while you are drilling, you might induce losses, and that losses can lead to a kick. So this is a typical issue with certain conventional drilling scenarios where you have a narrow operating window, narrow margin between pore pressure and fracture gradient. Now what MPD does is, you can plan in such situations, you can plan your static mud weight at your pore pressure, as you can see here in the second plot with the green curve. And when you apply surface back pressure, you will see that there is you are well within your margins. And as we go along, we will see how this happens, how this works. And now let's talk about underbalance drilling, just for the purpose of comparison. Now you see in underbalance drilling, the blue line on the extreme right side, you will see that the static pressure is way below your pore pressure. Now this gives you a very good idea about when you plan to drill a well in a particular way, how you plan your mud system. And this is pretty much the job of a drilling engineer to decide what is going to be your mud density in a particular well. And he does it based on certain calculations and by referring to the pore pressure and fracture gradient data. So basically the difference between UBD and MPD is that UBD, where we have hydrostatic pressure, is designed intentionally to be lower than your formation pressure. Whereas in MPD, your hydrostatic pressure of drilling fluid is designed to be at balance or marginally overbalanced. In most cases, it is marginally overbalanced, because to know exactly what the pore pressure is at any given point is not very easy. So based on the estimation, you usually plan with a slight margin. In conventional drilling, you definitely have a higher margin in order to ensure that you don't get any well control or you don't get any influx of formation. So the objectives of MPD and UBD are different. MPD is mainly for optimizing drilling to drill in formations that are not drillable, whereas UBD, you drill under balance in a way that you actually produce while you are drilling. So you do reservoir characterization and you ensure that there is no formation damage, produce while you are drilling in a way that you get the formation fluids to surface, you separate them, you do analysis while you are drilling, and you get an idea about the productivity of the well while you are drilling, even before you run the completion. So wellbore pressures, let's talk about wellbore pressures. What pressures are we trying to manage here? Now, the commonly known pressures that we have here are basically your pore pressure, your fracture pressure, and your collapse pressure. There's also one more pressure, which is your overburden gradient, but that is your maximum, basically stress, vertical stress in the wellbore. But these are the three main pressures, and you can see in this plot here, they are represented in your pressure profile. This is also called as drilling window. Now, these are the pressures that we cannot manage. You can only determine them using calculations, but you cannot manage these pressures, and they are given to us. There is uncertainty associated with these pressures. As you can see, when you do some estimations, you will notice that you have three values of pore pressure, you have three values of fracture gradient. So this is a challenge that usually as petroleum engineers, as drilling engineers, we are faced with to determine which would be the correct one. And now there are the other pressures that we have in the wellbore are the hydrostatic pressure and the friction pressure that we just spoke about. And we can manage these pressures, we can control these pressures in the wellbore by either changing the drilling fluid density or by changing the pump speed, the circulation rate. So the more, and of course, the other properties of your drilling fluid. And we will see this in more details as we go along. So what is a drilling window? I mean, we hear this term drilling window. A drilling window is essentially nothing but your difference between formation pressure and fracture gradient. As you can see here on your this curve here, at the bottom is a representation of your formation pressure. This one here is your fracture gradient. And here in this example, the drilling window is large. It's considered to be large. So when you have a large drilling window, if you have pressure cycles in your well, you will still be within the drilling window. Now, what happens if you have a smaller drilling window? So let me just move to the next slide. So if you have a smaller drilling window, so now here in this scenario, you will see that when the pumps are off, you lose your friction pressure, and in the well you only have hydrostatic pressure. So in that case, your pressure goes down, but since you have a large window, you are still within that window, and you are not, your pressure is not below your formation pressure. So what if we have a small operating window like this? And this typically you would see in deep water environment or in certain high pressure, high temperature environment where you have very high formation pressure approaching your fracture gradient. So when your pumps are off, in this situation, you go below your formation pressure, and in this case, you may get two possible, situations, two possible issues that can happen. One is your influx of formation, fluids, or you can get wellbore instability. If your formations are unstable, then they will not be supported with lower pressure, and you can experience wellbore instability. So this is the difference that we need to keep in mind, and this can change during the course of the well in a particular subsurface environment. Now let's see in real life how a typical drilling window looks like. So this is, as I have shared this plot before, you can see that there are, as you go deeper in the well, your pressure profile narrows down. So this, let's say at proposed TD, you have basically very, very narrow window. And if you plan your mud weight, this red line is just an indication of what typically your mud weight should be. It could be either here, which is in the middle of the two lines, or it could be here, which is, if you consider the mid case, pore pressure mid case. So in any case, there is uncertainty in your planning, and if you're planning with this scenario, you may, and if your pore pressure ends up being on the PP high range, high scale, then you may end up definitely having problems in the well. So what uncertainty are we talking about, and what did we notice in this plot? What we noticed in this plot was there is some uncertainty, and this is what we typically see in when you are planning a well. So the answer, you have two cases, low case and high case, where there is an uncertainty of around 2.2 ppg. You also have uncertainty of in fracture gradient of about 1 ppg, and the overall window uncertainty is 3.2 ppg. So this kind of uncertainty can create issues while designing your mud system, but MPD can certainly aid in this, as you have an option to adjust the pressure in the well while you are drilling, and if your estimation doesn't turn out to be accurate. So the goal of MPD is to use a closed and pressurized circulating systems. How do we do this? We use a closed and pressurized circulating system to control the pressure in the well, throughout the well. Thus, it eliminates certain issues like wellbore instability or influxes from the well that can happen in conventional drilling. So there are typically these 4 variants associated with MPD, so that we know what we are referring to as MPD. One is the return flow control, where you don't do any generally pressure management, but you just control the flow of fluid in the well. You divert it away using a closed system, so you do not have any exposure of hydrocarbon fluids to the people working at the rig floor. You close the wellbore, but it will still allow you to move the pipe as well as rotate it using the RCD. There is a method called constant bottom hole pressure, which is the most common method that we have seen, and the constant bottom hole pressure would essentially mean that you manage your bottom hole pressure and compensate for the loss in ECD, or you adjust your pressure using surface back pressure. And we will see these things as we go, how we do it. Another method is dual gradient drilling. The dual gradient drilling is basically uses 2 different fluids to control the well. This is mainly used in deep water, where you manage your pressure by, you have a different fluid in the riser versus what you have in your wellbore in the annulus. So typically used in dual gradient, but it's also a function, also one of the variants of managed pressure drilling. And then you have pressurized mud cap drilling. It's important to know all these terms, because sometimes you will be asked to, basically a company would decide that we just want to use this MPD for return flow control. We are not going to do any pressure management. So in that case, you would still have an MPD system set up on the rig, and in case you might be wondering, what are we doing? So here the company is only, and I've been on such jobs where we are just managing, we're just monitoring the well. We're just monitoring the returns from the well, and we are not doing any pressure management. So, but that is what the objective is for this particular thing. So the last option is, for example, pressurized mud cap drilling. Here, this is used in total loss, extreme loss situations, where you drill in, again, in offshore environment, where you have fractured carbonate reservoirs, where these fractures are so big that you lose all your drilling fluid. So in that case, you use sacrificial fluid in the well, which you continue to lose, and then you have a cap fluid in your annulus that you fill with, and then you manage your pressure in a way that you balance it with the cap fluid and your sacrificial fluid that you continuously pump in the well without any returns to surface. But you manage your pressure in the well such that you don't get any kick from any other formations, smooth formations. So these are the 4 variants of MPD, and each one has its own application, and we will discuss them. So this is how a typical setup of MPD looks like. You'll see here, you start with the rotating control head, then you have your choke manifold, then you have your Coriolis meter, which does the kick detection. Then you have this is the annular preventer, just to give you an idea about the BOP stack. And this is your mud gas separator. So typically these are the key components, but in the real scenario, the setup is quite complicated. You have a number of valves. They all need to be numbered and operated from time to time in order to line up a particular flow path. So how does constant bottom hole pressure technique work? So this is your pump on scenario. What happens when you switch off your pump is you lose your friction pressure, as we just discussed, and then it might so happen that you go below your pore pressure basically pore pressure value. And with MPD, you can essentially move this within your pore pressure value by increasing your back pressure. So this is what we typically do, and this is one of the main applications of constant bottom hole pressure, where we adjust the back pressure when we need it, to ensure that it is your pressure is within your pore pressure and fracture gradient profile. And now the other thing that you might have heard about is enhancement of peak drilling with MPD. So how does it happen? What do we do? What happens in MPD and how does it enhance peak drilling? Let's have a quick look at it. So MPD enhances your primary well control. Yes, this is true, and it has been additional processes that we have been discussing about. So typically in conventional drilling, how is a kick detected? Now, usually we all know that the sign of a kick is basically increase in flow out. Now, monitoring of flow out in conventional drilling is done using a flow paddle which is installed on a flow line. Now, this is a sensor which detects deflection in this flow paddle and it converts it to a signal. Usually the sensor measurement is relatively inaccurate and it just gives you a measurement between 0 to 100% flow. So during this, and he needs to make an informed guess on whether he's getting a gain. And then if he gets some indication, correlates it with the gain in the pit, he usually stops drilling and does a flow check to see if the well is indeed flowing. Again, the flow check is to be determined by this paddle as well as some increase in the well in your pit volume in the well. So now with this, these methods are relatively inaccurate because this sensor requires regular cleaning, maintenance. If you're drilling with water-based mud, it usually tends to get stuck, and the fluctuation on the calibration will never be so accurate. So you always have a difference of 15 to 20%, and then you tend to lose accuracy and pick up small signals with this kind of a sensor. Therefore, this is in conventional drilling, kick detection is usually very difficult. The other thing that we do is the mud density measurement is done usually using this instrument, which is called as mud balance, and it is done manually periodically. So if there is a change in mud properties, you'd only know when your man at the pit takes a sample, your mud engineer does a measurement, and then they report this. Basically, sometimes it is not as frequent and you would miss some indications early. And pit level. This is another thing you see on the right side of your screen. This is basically a sensor that measures your pit volume. Now, you guys all might have heard about an indication of gain or a kick is usually increase in pit volume. So how do we know whether there is an increase in pit volume is you have a sensor like this mounted on each pit. Now on a big drilling operation, you have several pits and you have multiple sensors, and there are a lot of transfers sometimes being done from reserve pit to active system or vice versa, and sometimes you can miss some indications or some indications might be misrepresented. So these could potentially delay detection of a kick or an influx, or you can miss some indications and therefore it is not very accurate. What do we do in MPD differently? So you see you install a Coriolis meter in your return flow in MPD, and we saw that in the flow diagram a little while ago that right after the choke manifold there is a flow meter. This flow meter measures density and flow rate. The same device gives you accurately a value of density and flow rate. And the measuring principle of this is available. We may not be able to go through it in details here today, but it's a good subject of discussion in case somebody is interested. And a number of manufacturers are there out in the market to provide this device. There is an application selection needs to be done based on the flow rate, at what flow rate you will be circulating, 300 GPM, 400, 500, 600, depending on the whole section, depending on the volume, depending on the cuttings. So there, there is a big area of work over here where when you select the equipment for a particular job. Now, this sensor basically one device that measures flow rate, density, and temperature. And essentially, you are actually monitoring flow out continuously in your unit of measurement, that is gallons per minute if you are using field units, and you keep comparing your flow in and flow out all the time, and you see if you are getting any influx or losses from the well. So this is how you typically monitor your operations with MPD, and it increases the accuracy. So a small change can give you an indication of something deviating from the normal trend, and then you have an opportunity to go back and check if anything is going wrong and not wait for the pit volume or some other indication in the well or the mud balance or the mud measurements done by the mud engineer to check. So you know basically through this meter whether there is a change in the density, meaning if there is any gas entering in the mud, or if there is any losses downhole, and so on. So this was how basically MPD enhances kick detection. Let's quickly look at the MPD equipment. Although we are not planning to cover this in details here in this session because the main objective is to discuss about well design. So this is a typical MPD setup on the rig where you see conventionally you would just have a flow line. The dotted line here that you would see would be just a flow line and the paddle type sensor mounted going to the shakers. But MPD, it introduces additional equipment. You have your choke manifold. You have your Coriolis meter that we just spoke about. Choke manifold is used. You have your RCD that closes your annulus. And you have a rig pump diverter here in this diagram. This is Halliburton equipment which is used. And we will discuss about why we need it. But one thing is important to know is that you need to have when you are applying back pressure, then it has to be flow through the manifold, at least a minimum value of flow in the system. So this needs to be maintained. This is maintained using rig pump diverter. This is a typical RCD from Weatherford. This is another one from, these are different models. According, if you see here, there are different pressure ratings and for different applications. And depending on your application, your well, your pressures, you can choose one of the RCDs. If you are not going to experience very high pressure in the well, then you can use a low pressure RCD. This is all part of the design work that you do. You know how much surface pressure you are going to see. And there are working pressure. And one more thing that you should notice here is that there is working pressure. And then there is static pressure. So when the device is static, it has got higher pressure rating. When you're rotating and you're moving the pipe, then there is another pressure rating. So each device, as you can see, and it's important to note that has its own pressure rating. And then at the bottom here, I have mentioned ID, that is internal diameter. ID is also important because if you are having particular tubulars that you are going to strip through it, then the RCD should be able to accommodate those devices. So in that case, you need to be aware about this fact. Now here there is another specification from a company called Pruett. They make RCDs as well, and they will provide you all the application engineering. If you give them your tubular specifications, your RPM, your pressure that you are planning, you're expected to encounter. The height is important because it needs to be mounted on the rig above the BOP, so the areas, the space above the BOP should be adequate to accommodate a particular RCD. So all these points are important when you modify your setup on the rig. And this is all part of the well design process. And if you are having an offshore application, then this is how the setup is in offshore environment. Your RCD is installed below your tension rig. So in your marine riser, and from there it is the fluids are routed to your control system. And just wanted to play a video. This was from a company called Fluid Optimum Pressure Control, which is a leading MPD service provider. Most of you might be aware about it. So this is a very good animation to give you an idea about an entire MPD process. So here you can see it's right in the beginning when you install the RCD bowl. Now this part is only the RCD bowl, and you're hooking up your flow line to the RCD. Now this is the bearing assembly. These are some of the components that you should be familiar with. For those who are already familiar, this is just a recap, and probably the animation will give some idea about how it's done on an onshore location. This is a control unit for RCD that is used to close and open the RCD. So once you install the bearing assembly, RCD needs to be closed, secured. This is the complete footprint of the equipment. As you can see here, the blue part is all we have as an MPD equipment. The rest of the gray one is the rig setup. Now you start your operations and your fluid is being circulated to the well as you normally do it in any drilling operation. But what changes is the process at the surface.
Say it's all right. Say it's all right. It's all right. Have a good time. 'Cause it's all right. Oh, it's all right.
Now the mud is returning from your RCD into your flow line. It goes into your choke manifold. And that's the Coriolis meter. This is the manifold, and this is how it would look from inside. That's your mud gas separator. In case if you're having gas in the well, you would typically use that, and that's your flare. This is your control system. HMI is a human machine interface. So this is where an MPD operator or an MPD engineer would typically be working using a control system and a display on a industrial computer. So now you see here there has been a increase in flow rate. It was detected, and this gentleman here, he's now doing some adjustments. He's changing the set point to close the choke. By closing the choke, he has managed to contain the flow, and you can see that the flow has reduced, and then operation is now being returned back to normal. So this is how it is. This is how a choke looks like from outside. This is how a choke manifold looks like from outside. There are many different companies manufacturing this, different sizes. Some of them are compact, some of them are big, depending on your applications and kind of circulations that you're going to have. And the main function of the choke is to maintain, increase and decrease your surface back pressure. As we just saw in that animation, you can close the choke by and increase the pressure, or you can open the choke and decrease the pressure. And then maintain constant bottom hole pressure. There have been electrical chokes right now, so they are more accurate. The response time is fast, the failure rate is low, and a lot of developments are going on in the industry, and it is important for all of us to keep a track of this. Flow meter, we already discussed about it. This is how a skid flow meter would look like. The actual flow meter is part of the manifold, and the manifold has got valves. So in case if you want to replace the flow meter, you have to route the flow through another path to ensure that we can replace it and change it in case if there is a failure or some kind of debris that is stuck in the flow meter. And this is how it looks like otherwise in a different case. So now this is an important thing. Non-return valves are installed in drill string, and the purpose is to prevent backflow of fluids from the well into through your drill string to surface. Remember that your drill string is your shortest path of wellbore fluids or kick coming to surface because it is very narrow. It has got a very smaller ID, so it needs to be protected. So these type of NRVs are installed in the drill string. It is mandatory when you are dealing with MPD. These drill string valves are installed even when you are not using MPD, but it is pretty much very important, and we need to have two NRVs. This is something that the BHA will normally have, but you should be aware about it. And what is the planning process? I mean, how does it go and now that you have decided to use MPD on a particular well? So an engineering evaluation is done when you collect drilling data, subsurface data. Then an MPD program is prepared, which takes about 2 to 3 weeks after analyzing and deciding the methodology of an MPD process. And then the MPD engineer usually passes on that MPD. Once the program is approved by the client, it is passed on to the project manager who actually focuses on the operational side of it. What are the inputs that you need? You need pore pressure, fracture gradient, you need wellbore geometry. Basically, you need just these parameters to get started with your MPD program. You need the drilling fluid design and the drilling fluid properties, the rheological properties of drilling fluid. You need your bottom hole assembly that you are planning to use for the particular section, and most importantly, drill pipe information, the size, the OD ID of the drill pipe. You need the temperature profile because that will have an effect on the fluid expansion and contraction. If you are having high temperature, it has an effect on your fluid properties, fluid densities, and this needs to be compensated with surface back pressure. You also go through your offset well data, drilling reports to ensure that there is if there had any issues in one of the previous wells, and if so, at what depth these problems were occurred. So you can be vigilant about similar situation in this particular well. So reading drilling reports from previous well is very important. They will give you a lot of information, and you can accordingly plan for the current well and how MPD can support these challenges. And the logging data is usually essentially important for various reasons. Your pore pressure fracture gradient data comes from the logging data. Logging data also provides hydrocarbon, water, any other zones that are there in your drilling interval, so that you know. And project manager basically in any MPD operation is responsible for getting the equipment ready, mobilizing the equipment to the field, basically assigning field personnel for a particular job, carrying out rig inspection. It is important to carry out rig inspection. Rig inspection will provide you information about the interfaces that you have with the rig. Then you have a PNID that is prepared. For those who don't know what is PNID, PNID is a process and instrumentation diagram. It has got all the information about the process that will be deployed. Basically, like for example, the different valves, isolation valves, type of valves, starting from your RCD all the way up to your flare stack or shell shaker, and multiple paths. And one of the planning process involves conducting hazard and HAZOP meeting at your client's office, and also involving other service companies who would be present during this operation and the drilling contractor to discuss about the various hazards and to make sure that they are mitigated or addressed, controlled or mitigated properly. So usually when the operation commences, you have project manager, project MPD engineer. They usually oversee the operations and implementation. After the operation is completed, an MPD engineer would typically complete end of well report and ensure that and analyze whether all the KPIs of the particular MPD projects were met. Key performance indicators of what was the objectives and whether our objectives and key indicators were achieved or not. So this is typically from start to end how a process is completed in a very broad way. Specifically, this takes a few months, if not several months to complete. And then once the more better planning you do, the better outcome you would have. You know, in summary, basically, we use MPD for improving safety and well control. You improve peak tolerance and you manage your ECD.